Welcome to another in my series of videos on control systems engineering. In this video, we'll talk about designing PI, PD, and PID controllers via root locus. There was a previous video on using P-only controllers and designing the control gain via root locus, and now we'll see what happens if you want to go beyond that. The thing that's different about these other types of controllers compared with the P-only controller is that the P-only controller does not modify the root locus of the existing system. What happens there is when you adjust the proportional gain, the P gain, it actually moves the closed loop poles along the root locus to different locations. So you can change the way an existing system behaves simply by changing that gain. Again, to understand that, you need to go back and look at the P-only controller design using the root locus. Now, to understand how a PI or a PD changes the root locus, you need to look at the structure. We need to look at the structure of those controllers, and that's what we're going to do specifically in this video. Once you understand both the PI and the PD effect on the system, a PID is really nothing new, because a PID can be looked at as a PI with a D component added onto it, or a PD with an I component added onto it. So a PID is nothing beyond those two things. Now, before we get into this and start talking about the effect of the I component and the D component on the loop, it's worthwhile to remember where the controller is in the loop. And GC in this picture of a basic loop structure is our controller. And we will be talking about that explicitly later on in the video. We can simplify this, though. Well, first, before I go into that, what I need to explain is that we are going to look specifically at this one little block in the control loop, in the closed loop control loop. But remember how the controller works. It takes in a signal called the error, which is the difference between your desired value and your measured value. This is the actual value in your sensor. So this is your measured value, and it compares the two simply by subtracting them and produces an error. And then that error goes into the controller, and the controller decides what to do with the error and puts a signal out to the actuator that then moves the plant. This is the plant, the thing that we're trying to control. So the input signal is the error, and the output signal is the signal going out to the actuator. But we can simplify this loop, and to make our example as simple as possible, that's what we're going to do. What we shall do is we shall combine the actuator and the plant into one big system. And then the other thing that we're going to do, you can't see anymore, the sensor is here, is oftentimes nowadays with computer control systems, specifically, it turns out that the transfer system, the effective transfer system for the sensor is 1. So we will see how this works. Here I've combined the actuator and the plant into one big transfer function. Since they're in series, we simply multiply them by each other. And then the other thing that I've done is I have made a unity feedback system, it's called, because the sensor has a effective transfer function of 1. And this is a further simplification. Now let's look at the sensor first. That's the simplest one to contend with or to deal with. We have like I said, an effective transfer function of unity. And remember how transfer functions work. It takes the input and multiplies it times the content of the block and then puts that on the output. Well, if 1 is the content of the block, it's simply getting the input signal and putting it on the output, which means you really don't need this block here. And so we have what's called a unity feedback system here. Then what I've done, now this is going from general to particular. I have said that combined, I have a first order system, and this often happens too, where I've replaced the GA and the GP with this first order system that has a gain and a time constant here in the denominator. Now this is not the general case, this is a very specific case, but it's a very common specific case. So we're going to use the commonality of this to make a simpler system to talk about as an early example here. Okay, and I've said all this already, so I'm not going to repeat it. Okay, what's important here, though, with our simplified example, is that we are going to be talking simply about this part of the loop itself, the controller, and what happens when we add an I part and a D part to our controller. We'll start with a P controller only, and then add an I part or a D part, and then both eventually, and see what happens to our system. So what we're focusing on here is we're focusing on the controller itself. Remember, the input is the error and the output is the actuation signal coming from the controller. So with all that said, we can go ahead to our discussion of this. We'll talk about the adding the I part first. And again, here's our controller. As you can see, there's the E coming in and the actuation signal coming out. And the way that a PID controller is structured, or a PI controller is structured, is you have a P path and you have an I path. So what happens is we get the error and just feed it directly into the proportional gain of the controller, and it produces what's called a proportional action. What happens here, and I don't want to go into detail on this because I covered it elsewhere, is we actually get the error signal and we integrate it. So what we're getting out from there is we're getting the area under the error curve. That's a funny way to say it, but it sort of encapsulates it all. It's the area under the error curve, and then we multiply it by the integral gain, it's called, and that produces an integral action. So we have two actions here that are combined, a P action and an I action, and those together form the total signal that goes out to the actuator. Okay, now if we look at this, the transfer function for this whole thing here, notice what I've done is I've added the proportional part and the integral part. The integral part is gotten, since these are in series, it's just Ki times 1 over S, which produces Ki over S. And then if I just use a little bit of fraction algebra, I see that I get a transfer function like this, and then I can manipulate it algebraically a little bit more, pull a gain out, and what you can see here that we have, what we have added to the system. Remember, the controller is just being put onto the entire system. What we have added here, though, is we have added a pole at the origin. That's the S there in the denominator. We have added, oh wait, let's see, I think I do this next, so let me click here. So we have a pole at the origin, and then we have a 0. It's a 0 since this is in the numerator of the fraction, and this 0 is at minus Ki divided by Kp. If I put that value into here, it will make this whole thing in parentheses 0, and that's called a 0 when it's in the numerator. And then the third thing that we've added is we've added a gain in front of all that. So by adding a PI controller to a system, we're adding three components really: a pole at the origin, a 0 at this particular location given, and then a gain. Now this changes the root locus of the system. Remember, when we had only the proportional part, it did not change the root locus of the system, because the open loop transfer function was simply when you added the controller, was the old open loop transfer function with the gain added in front of it. But now we have added all of this in front of it. So the open loop transfer function of the system has changed with the addition of this 0 and this pole at the origin. So we'll see where that takes us. So before, if we had the first order system that I showed as the actuator plus the gain, we had an open loop pole at -1 over t. And if you put a P-only controller in it, you can actually, well, the root locus looks like this of that system. If I put a P-only controller in there, I can actually move the closed loop pole along the root locus. But what I've done when I've added a pole at the origin and a 0 out here is I've changed the shape of the root locus altogether. This could be good or it could be bad, okay? But the point is that if we had a P-only controller, we could not change the structure of the root locus, but with a PI controller we can, and we do. Okay, let's look at a PD case. A PD is like a PI, except rather than adding an integral path, we add a derivative path. So we take the error and again feed it through the P part. It's a proportional action, it's called. But then we take the error also and we differentiate it. So what we're getting here is the change in error at any particular point in time. And what that means is if you look at the error curve as a function of time, what this is this is the slope of that error curve. So the more the error is changing, the greater this value will be. And then we multiply it by the derivative gain and add that into the proportional gain, and so we have a PD controller, and the combination of those two signals is the signal that goes out to the actuator. And then if we look at this, we get the transfer function for a PD controller, simply Kp plus Kd times S. And we can manipulate that algebraically and see that what we have now is we have a 0 at this value right here, negative Kp over Kd, because if I put that value into here, it makes this whole thing 0. This is in the denominator, there, or the numerator, sorry. There is no denominator, so this is a 0, this is in the numerator. So we have a 0 there, and we have a gain in front of that. So the PD controller is actually simpler than the PI controller. The PI controller is like the PD controller, except it also has a 0 at the origin. But the point is that this changes the root locus of the system too, and if we want to see how that happens, here is the root locus of this first order system with only a P controller. But when we add the 0 at the origin, or not the 0 at the origin, excuse me, the 0 at Kp over Kd, negative Kp over Kd, then we have a system where rather than the root locus running out to the left as it does here, if I make this number less than negative 1 over t, the root locus will head towards the origin rather than away from the origin. Of course, I could have put Kp over Kd. I can choose these so that I put this out further to the left, and then it would run out to the left, but it would not run out infinitely like it does here. It would stop at the 0. Okay. In this particular case, if I put I put in Kp over Kd as a smaller numerical value, then well, let's see. If I put negative Kp over Kd between the origin 0 and negative 1 over t, what happens is the root locus will go this way, and as you turn that gain up, it will actually make the system get slower and slower and slower, because remember on a root locus plot of the complex plane, if you go to the right, if you go towards the origin, you're getting slower. Okay, now if we put them all together, the proportional gain, the integral gain, and the derivative gain. So we have 3 paths rather than 2. That makes it still more complicated. So if we look at that, I've simply gotten the transfer function for a PID controller. Here's the proportional part, here's the integral part, and here's the derivative part. And I can use a little bit of algebra and combine all these into an overall transfer function for the controller like this. And as you can see, I have a second order in the numerator, and then I have a pole at the origin. Okay, let's click through here. So 2 zeros, that makes that a second order. There's zeros because you're in the numerator of the transfer function rather than in the denominator of the transfer function. Okay, now you can add these zeros wherever you like. They can be either real or complex, and it just depends upon what you choose as values for Kp, Ki, and Kd. So this is just an introduction into how the I part affects the transfer function of a system, and how the D part does, and then how both of them together do. And that's going to be the end of my video, of this video. Stay tuned, there's more to come. Thanks for watching.